Welcome to The Explainer. I want you to take a second and imagine looking up at a perfectly clear, incredibly dark night sky. You see thousands of twinkling points of light, right? It's this breathtaking display of cosmic beauty. But here's the crazy thing. When you look at that sky, you are literally only seeing the closest, immediate neighborhood of our galaxy. The true scale of the universe is almost entirely incomprehensible to the human mind. And yet, paired with that unimaginable vastness is a deafening, haunting silence. No radio signals, no sprawling alien empires, no cosmic hello. It's the ultimate detective story of our cosmos. And today, we're going to explore the profound mystery of why space seems so incredibly, stubbornly empty.
Look at this number, 70 sextillion. That staggering figure is the estimated amount of stars in the observable universe. To put that into perspective, our Milky Way galaxy alone holds roughly 200 to 400 billion stars. Now, with a really high degree of probability, many of these stars are way older than our Sun, and a vast number of them have Earth-like planets orbiting right in their habitable zones. The raw materials for life are scattered abundantly across 70 sextillion solar systems. It's absolutely everywhere.
And that staggering scale brings us to a really fundamental contradiction. Because if we assume the mediocrity principle, the idea that Earth is just a typical planet in a completely typical star system, then mathematical probability dictates that we absolutely shouldn't be alone. In a 13.8 billion-year-old universe, intelligent life should have evolved elsewhere, long ago. Some civilizations should have already developed interstellar travel and spread out throughout the stars. Yet, when we scan the cosmos, nothing. We see absolutely no evidence of alien life.
Okay, let's dive into this with Section 1, the Los Alamos Lunch, a 1950 conversation.
So, this cosmic puzzle didn't actually begin in some high-tech observatory. It started over a casual summer lunch in New Mexico, back in 1950. Enrico Fermi, a Nobel Prize-winning physicist, famous for his work on the first artificial nuclear reactor, was walking to lunch at the Los Alamos National Laboratory. He's with some incredibly brilliant colleagues, Emil Konopinski, Edward Teller, and Herbert York. They were just casually chatting about recent reports of flying saucers and whether faster-than-light travel was even feasible. The conversation eventually shifted to other stuff while they ate, but then Fermi suddenly just blurted out of nowhere, "But where is everybody?" And the amazing thing is, everyone on the table instantly laughed because they all knew exactly what he meant without him having to explain a thing.
Now, Fermi wasn't just making a casual joke. He followed up his question with some rapid, frankly astonishing mental math. He calculated the probability of Earth-like planets, the rise of high technology, and the time required for cosmic expansion. He figured out that even if an advanced civilization traveled at just 1/100th the speed of light, which is actually a pretty sluggish pace in the grand cosmic arena, they could explore or colonize the entire Milky Way galaxy in roughly 10 million years. And in geological and cosmological terms, 10 million years is just a blink of an eye. The galaxy should have already been colonized multiple times over. So seriously, why haven't we been visited?
The author Douglas Adams hit the nail on the head when he wrote that our brains simply struggle to comprehend massive cosmic distances. Space is just profoundly huge. Because human intuition completely fails us when we try to grasp billions of stars in millions of years, scientists realized they actually needed a structured mathematical framework to break down the real probabilities of life emerging elsewhere.
Which brings us to Section 2, the Drake equation, formulated in 1961.
In 1961, astronomer Frank Drake came up with this elegant equation to evaluate these massive cosmic probabilities. What's really fascinating about this formula is watching how our scientific certainty changes as we move down the list. So it's a product of 7 variables. The first 3, the rate of star formation, the fraction of those stars with planets, and the number of planets with suitable environments. We're actually getting really good at estimating those thanks to modern astronomy. But as we move further down the list, going from the fraction where organic life appears, to intelligent life, to civilizations that broadcast detectable signals, and finally how long those civilizations survive to broadcast, our scientific certainty drops off an absolute cliff. Those final 4 variables are currently complete, utter unknowns.
We can actually see how the beginning of this equation builds using physical evidence. Take a look at Kepler 452b. This is an artist's conception of an Earth-sized planet sitting squarely in the habitable zone of its star. So we know for a fact that potentially suitable environments exist out there in the galaxy. But knowing a planet is there is very, very different from knowing if the spark of life actually caught fire.
Abiogenesis, which is that gradual process of increasing complexity from non-living chemicals to self-replicating molecules, remains a massive mathematical mystery to us. And this brilliantly illustrates another profound unknown. On Earth, life is structurally based on carbon. It uses water as an interaction medium, and it relies on processes like photosynthesis, which requires energy transport from a hot object, like our sun, to a cooler object. But we aren't even sure if these chemical requirements are universal constant. Are carbon and water absolutely necessary everywhere? Or is there this wide range of atomic possibilities in extraterrestrial organisms? We literally just do not know if life universally requires the Earth-like chemistry we see here.
Let's move on to Section 3, the Great Filter and some existential resolutions.
Since the math suggests we absolutely shouldn't be alone, but the skies are completely empty, we have to look at some potentially terrifying resolutions. We're going to start with a really thought-provoking concept introduced by economist Robin Hanson in 1996, the Great Filter. This idea suggests that at some point in the evolutionary chain, from a habitable planet forming all the way to a spacefaring civilization, there is a step that is exceedingly improbable, or maybe even impossible to pass. And here is the truly terrifying part. We have no idea where this filter is. It might be behind us. Maybe the jump from single-celled organisms to complex multicellular life is astronomically rare, and we're just the incredibly lucky exception. Or, more ominously, the filter could be ahead of us, meaning civilizations frequently arise, but they inevitably destroy themselves through nuclear war, resource depletion, or rogue technology before they can ever colonize the stars. Okay, but before we get entirely too gloomy, let's look at a slightly more optimistic resolution from astronomer Jill Tarter. Some people criticize the search for extraterrestrial intelligence, or SETI, calling it a waste of time, just because we haven't heard anything yet. Tarter brilliantly counters this by pointing out that humanity's search has been incredibly brief and super limited. When you consider the vast number of stars and radio frequencies out there, trying to conclude that the universe is empty based on our tiny little searches so far is exactly like dipping a drinking glass into the ocean, looking at it, finding no fish in the glass, and concluding that the ocean has no fish.
That brings us to Section 4, Grabby Aliens and the Physics of Light.
In 2021, Robin Hanson and his colleagues introduced a theory that views alien civilizations through the completely uncompromising lens of cosmic expansion. This theory essentially splits extraterrestrial civilizations into two camps. First, you have quiet aliens. They stay put, they're incredibly hard to detect, and eventually they just fade away. On the flip side, you have grabby, or loud, aliens. They expand rapidly, they visibly colonize their surroundings, and they effectively prevent other civilizations from emerging within their sphere of influence. The logic here is pretty brutal, but clear. If grabby aliens exist, and they expand outward, our universe should theoretically be overflowing with their highly detectable, visible expansion. Which immediately prompts what might be the most crucial physics question of all. If loud, rapidly expanding alien empires are out there spreading across the galaxy at near the speed of light, why on earth is the night sky still completely empty? Shouldn't we literally see them coming toward us? Well, to answer that, we have to understand our past light cone. See, when we look out into the universe, we aren't seeing things as they are right this exact second, we are observing only our past light cone. Light takes time to travel. As writer Casey Hanmer points out, if an advanced grabby alien civilization is expanding toward us at a high fraction of the speed of light, the light carrying the visual information of their approach is traveling just barely ahead of their physical spacecraft.
Let's actually run the numbers on this timeline to see exactly how startling this really is. Imagine an alien spacecraft departs from a star 1,000 light-years away, and it's traveling at 99.9% the speed of light. Because of relativistic time dilation, the crew on that ship subjectively experiences a trip of only 45 years. But for us here on Earth, we wouldn't even see the light of their departure until year 999. And then, at year 1000, the spacecraft itself physically arrives at Earth.
What this means is that an alien empire could have launched a massive fleet heading our way centuries ago, and because they're traveling so fast, the light warning us of their approach simply hasn't reached our telescopes yet. The window between humanity realizing we aren't alone and the aliens actually arriving at our doorstep is vanishingly short. We wouldn't have centuries to prepare, we would have at best a few years or maybe just months. The phase of knowing they exist before actual physical contact is basically non-existent.
So the crucial point is right here in Section 5. Are we alone? The ultimate question.
So, how do we synthesize all of this? We started with a universe overflowing with potential and ended with a galaxy defined by its terrifying silence and the completely uncompromising laws of physics.
The takeaways from the Fermi Paradox fundamentally force us into a few distinct corners. Either the Drake equation's unknowns are so punishingly low that humanity is an incredibly rare spark of intelligence, or we're just incredibly early to the cosmic stage, and the great interstellar empires simply haven't formed yet. Or lastly, due to our limited search scopes and the relativistic physics of light, we are completely, fundamentally blind to an approaching civilization that is already right in our cosmic backyard.
Which leaves us staring back up at the night sky with an entirely new perspective. Earth's position in this massive cosmos is remarkably fragile. The silence we hear isn't necessarily peaceful. It might actually be a warning. We are forced to ask, if the Great Filter is still ahead of us, will humanity be the rare exception that finally breaks through to become a lasting interstellar civilization? Or are we, like countless others who may have come before us, already quietly running out of time?